Hello, my name is Whitney Hartsock. I'm in the Spring 2026 Physics 2211 class, and this is Lab 1, Velocity Predicted versus Observed. The purpose of this lab is to compare the observed position and predicted position. It takes in consideration real-world factors and ideal circumstances, how that affects the observed and predicted velocity of a marker rolling across a table. First, we should look at the fundamental physics concepts, especially Newton's laws of motion. The first law states that objects in motion stay in motion. This is relevant as we have an object rolling across a table at a constant velocity. The second law, force equals mass times acceleration, is the force applied, which is relevant because there is a force applied, and it's also relevant to the coding equation, which we will reference later. Finally, the velocity is the change in position over the change in time. Some fundamental physics equations are the velocity update formula, which is the final velocity equals the initial velocity plus the net force divided by the mass times the change in time. The position update formula is the same concept. In the real world, force is not constant, so we assume that the final velocity is equal to the average velocity. Also, you can see down below, these are the velocity and position update formulas in the coding form relevant to the variables that are put in place. We're modeling the position of the marker as it's rolling across a table and using VPython to calculate the resulting velocity. The system is the marker, the surroundings is the table, which is exerting a frictional force that eventually stops the marker, and the initial conditions are listed as follows. The reason that they're not all zero is because we had to trim the data in order for it to be most accurate. The marker is going faster at the beginning and slower at the end than the actual constant velocity, so by trimming the data, we have most accurate readings. This is a video of the tracker position data. This is done by uploading the video, marking the position of the marker as a point mass, trimming the data so that the motion is at a constant velocity, and making note of the trimmed initial positions and velocities. All of this is uploaded into VPython in order to get the predicted position as seen here. The predicted velocity is also calculated based off the given initial conditions. These are shown a little bit closer, the coding that goes into it. So as you can see, the initial mass, position, velocity, and time are all uploaded, as well as the calculation loop here on the right, where you can see the position and velocity update formulas that are put into those variable forms. For VPython, we insert the initial conditions provided into the Lab 1 starter code, listing the F-net vector as 0 because past forces are not relevant to current velocity. We'll talk about that in just a little bit. Then you put the position and velocity update formulas into the code in order to create the computational prediction models. Again, here these are for the third time. For the data comparison, you insert all of the time and position data from tracker, which is seen in the first video. Then you use the slope formula, change in x over change in y, to calculate the position. The slope of the position graph in the VPython code is 0.3x, where x is the time interval. Then you use Google Sheets to calculate the predicted position for the observed time intervals that are listed in tracker, and then you use the chart feature to compare the predicted and observed velocity. As you can see, they line up very well, and this is thanks to our trimming. As you can see, it's a little bit above our observed position and a little bit below at the end, whereas the predicted position is in a straight line. Finally, we have discussions and conclusion. Some possible error sources could be the predicted slope versus the observed slope. Friction is real in real life as a result of the table and the marker having contact, versus the predicted slope, which has an assumption that there is no friction. Additionally, the force is not constant, so it's a little bit faster at the beginning because that force is applied non-consistently, and it's a little bit different than it is at the end. And finally, inconsistent time intervals on tracker, because it's manually being predicted, it's not always going to be the same every time, which could result in a little bit of error. For the what-ifs hypotheticals, if we flipped the axis and had the marker rolling from left to right instead of right to left, the graph would be going in the negative direction. So here's what it looks like now, moving away from the x-axis in the positive direction, but if we flipped it, it would be moving away from the axis in the negative direction. Finally, for the what does it mean, the reason that the F-net is 0 is because the marker is in dynamic equilibrium. So the up and down forces, the force of gravity pulling it into the table and the normal force holding it up, balance each other out. The applied force of the push in the back is no longer relevant because it is a past force. Therefore, the frictional forces are also not relevant. They're assumed to be 0. So they're all at the net force equilibrium of 0. That is all. Thank you.